Hi, Suvrit, can you hear us? No, you are muted.
Yeah, yeah. I can hear you.
Great. So let us just wait for another couple of minutes for other participants to join, and then we will start.
Sounds good. Sounds good. Let's check if the screen share works.
Yes, please.
Ah, okay. Yeah, I'm having the trouble of the screen share to continue once you
No,
can
we
see
can now
something, right?
see. Yeah, we can see your slides now.
But the trouble is the moment I make this full screen, then the sharing gets disturbed somehow.
No, but we can see the full screen slides now.
Can you? How about,
Yes,
can you see the next
we can
slide?
see the next one, but the opening slide we can see. Are you changing the slides?
Yeah, because I think it says screen sharing gets paused. Somehow this used to happen to me previously. I see, I get it. You know why this happens? Okay. If usually you have more than one presentation open, I think my Keynote window has several presentations open. That's why.
Yeah,
Uh,
that might be the reason.
Sometimes this is a Keynote thing, I think. Let's try again. That's why yeah. Okay. Yeah, I think now it's all good. You can see the next slide also.
Yes.
Okay,
Yes. Now we can see
perfect.
the next.
I will-
Okay, so I think we are all set. Anish, shall we start?
Yeah, so we can begin. Yeah.
Okay. So good afternoon, everyone. This is okay. Good afternoon. This is going to be, I think, the final plenary talk in our almost 2.5 months long winter school on deep learning. And we are very thankful to have Dr. Suvrit Sra among us for this last plenary lecture. Let me introduce him formally and then we will fully on the show. Dr. Suvrit Sra holds the esteemed position of Esther and Harold E. Egerton Career Development Associate Professor within the EECS Department of MIT, USA, while also serving as a core member of both the Institute for Data Systems and Society, or IDSS, and the Laboratory for Information and Decision Systems, or LEADS. As a distinguished academic, he contributes to various esteemed research groups, including the Machine Learning Group, the Center for Statistics, and the TILOS AI Research Institute. Additionally, he plays a pivotal role as the co-founder and chief scientist of Pendulum. Currently, Dr. Sra is on leave as a professor focusing on resource-aware machine learning at the Technical University of Munich, broadening his academic reach. His research portfolio delves into the intricate mathematics underlying artificial intelligence, with a primary emphasis on optimization for machine learning, particularly in the realm of non-convex optimization, including non-Euclidean and geometric optimization methodologies, with notable interests extending to discrete probability, deep learning theory, sampling theory, convex geometry, and polynomials. Dr. Sra's outstanding contributions have been recognized with numerous honors, including the NSF Big Data Award, the Amazon Research Award, and the NSF Career Award. So now let us hand over the stage to him and listen to his plenary talk.
Okay. Thank you, Swagatam, for the introduction, and thanks to you and all the organizers of WSDL. So just in time for the talk, I actually just came back from MIT today morning. So luckily timing has worked out. And I'm going to hide the video screen here. Okay. So I'm going to talk about one currently exciting research topic that is going on for the theory of deep learning inspired by, as we all know, large language models. And this topic is something that is a very active topic, a hot area, and there's new research that comes out related to this topic very regularly. So I'd like to tell you one entry point into this topic, which comes from our recent research. But we continue to ourselves explore new questions in this area. So a high level way of thinking about this is you can think of this broad topic of understanding the theory of transformers or large language models, etc. One way to look at things is through the little bit of picture of geometry, to try to visualize what a complex model is doing. How is it learning? How is it performing this amazing inference? What's going on? And of course, we are theoreticians here, so we are trying to come up with good mathematical abstraction that we can analyze and understand. So the reason partly to do this is, of course, LLMs are super popular, and people have seen all kinds of amazing capabilities, but everybody's wondering, why do they work so well? And taking a geometric angle is more to help humans like us understand these very complex systems that are otherwise pretty difficult to nail down mathematically. And the work I'm talking about, actually, I decided to not talk about too many things related to this, but to focus, give you a clean picture, starting from, I think, one of our most important works on this topic. It's called Transformers Learn to Implement Precondition Gradient Descent for In-Context Learning. And I'll explain that carefully in this talk. And this work is done jointly with Xiang Cheng, who's a postdoc in my group, Hadi Daneshman, also postdoc, and Kwangjun An, a PhD student in my group. So the ultimate thing, if you want to just imagine where is geometry coming, you can just think that geometry, what we mean by geometry is whatever language we use here to discover structure in this complicated neural network or in natural language data and so on. And that's really the key aim of the talk. So let's get concrete here. So as you know, that LLMs, GPT style are built on GPT models, various versions of GPT. And the GPT architecture has in it the essential key component in that, which makes it have its power, is the so-called transformer block. So if you zoom in into a transformer block, the transformer is composed of some standard networks like this feed-forward network, normalization layers, etc. But the key component of a transformer block is so-called attention block. And you can have attention blocks in serial or parallel, and you get to then call them multi-head, single head, and so on. So for GPT, transformer is the essential thing. For transformer, the essential thing is the attention module. So let's zoom in to attention module. And you know from this famous paper that launched the transformer architecture is that attention is really the key thing. And an attention module consists of a few different parameters multiplying with each other, doing some softmax, etc. Why the attention module seems to be so powerful is a theoretical question. We'll partly answer that today, but you should, after listening to the talk, or maybe even before the talk, depending on what you've been thinking about, still be wondering that what is it that makes attention so special or so powerful? And so if we want to dig into understanding what attention is doing, why it could be so powerful, let's dig a little bit deeper. So let's make a simplified architecture that I'm going to talk about. So we came from GPT to transformer block. From there, we looked at attention as the crux. So for analyzing and describing what I'm describing to you today, we look at simplest kind of then transformer architecture. We just put this attention layer, attention in serial, and we put many of them. You get this deep transformer. We are ignoring the other things in there, okay? So let's just look at attention. And that's purely to make the analysis easier. Many of the other things can be captured in there. So this particular transformer, I'll call it a simple transformer, okay? And the key message, actually, I'll already give you the key message, kind of bottom line message of the talk here, is the simple transformer implements gradient descent. So what does that mean? Well, gradient descent is a widely used learning algorithm, right? And the thing that seems to be making, at least according to our theory, transformers so powerful is the forward pass of a transformer is itself implementing an algorithm like gradient descent. And that's why having an architecture that learns algorithms, that is what seems to be making it so powerful. But this is like not super rigorous mathematical statement, okay? It is true formally, provably in the setting that I'm going to show you. But you should be wondering at this point that out of all possible algorithms, why is the transformer that I'm talking about, why is it implementing gradient descent? Why not something else? It's a valid question. So keep that question in your mind as you think more deeply about attention and transformers. And when we try to study this idea through the lens of geometry, we gain some insights like, or merely this understanding that how transformer is implementing gradient descent. We gain some insights like, the attention module is what helps transformer adapt to the geometry of data. I'll show you later a picture what I mean by that. But this already suggests that attention is crucial in dealing with data that can come in various shapes. It could be, when you plot it, stretch thin out or like spherical or so on. And so the attention module adapts to that geometry, which is a very powerful feature. And now if you think of this transformer composed even of these attention layers, trying to understand how well is the transformer fitting your data, that's a tough problem. And so if you were to want to say that, okay, I've done this K-layer transformer, what is its approximation error? What's the transformer's error? How well is it provably mapping input data to output, right? Compute that. Well, that's really hard to compute, but the moment you see that each layer of the transformer can be viewed as implementing one iteration of gradient descent, then immediately your life simplified, because gradient descent is a simple to analyze method. So viewing that transformer can implement gradient descent as a byproduct helps you understand what is the error of the transformer as a map from input to output. It'll help us explain this crucial thing called in-context learning, which I will talk about in much greater detail. And on the way, then we'll understand attention and transformers a bit better, which can give us insights into designing potentially improved versions of attention modules or other architectures. And finally, with the hope that it may lead to better training algorithms. So to make it concrete, let's get back to this important motivation which actually started this whole process for us of why we are looking at in-context learning in particular and how we are understanding transformers. So we know that transformers based on these large language models, they're really good at this task, right? The standard task is predict the next word. So you give it a prompt, GPT-3 will predict the next word, and that's the output. It's really good at that. So what is in-context learning? So in-context learning means, if you don't know about it, you give it a prompt like here, apples are red, bananas are yellow, grapes are, and you leave a blank, and filling in that blank is the next word the transformer should output. And it manages to fill in the color purple so it seems that it may have actually done some learning. And if you give now similar prompt but a different output, like lemons are sour, cranberries are bitter, grapes are, and it's a different set of examples with a different expected. Oh, sorry. Sorry. Okay. So different set of examples and a different answer. And now you can see that how you architected the prompt. You put in some concept in there. So you're actually putting in examples, right? This can also be called few shot. And transformer is able to, or an LLM is able to give you an answer. So you can think of this as a learning method, because we gave data and you wanted the label, which is either purple or sweet here, right? And the crucial thing is, that's what in context learning, that the model is able to learn purely from these demonstrations without having to update its parameters. And that concept is called in context learning. So that's the crux, without changes to its parameters. Because if you think, for a transformer, in the end, this is just a sequence, right? Lemons are sour, cranberries bitter with those parentheses. For us, it's just a sequence and it's just outputting the next word. For us, the sequence has meaning. We view subparts of the sequence as kind of training data. And so one can, that's why, think of the forward pass prediction of transformer as just another way to do learning. And that gets to be called in-context learning. You can try this out. You can ask GPT other such things. You can give it examples of writing out 2 + 1 3, 3 + 1 4, and so on, and see if it can predict. Did it figure out you want to do addition? And in some cases it can, and you can try to understand why that is happening, and so on. So this really cool property of in-context learning is in fact, a very important property. It was first outlined in that famous paper of Brown et al. And given how human languages and human inference depend so much on contextual information, people believe that understanding in-context learning is the key to understanding why LLMs work at all. So this problem of trying to understand and explain in-context learning is one of the key theoretical building blocks to understanding large language models. So let's look at now this in-context learning a bit more closely. And to be able to understand it, I'll take a very simple problem class. Okay, so now let's try to look at the task of learning linear functions. So previously we had words, apples, bananas, grapes. The first layer of a transformer would embed each word into a vector. And then, of course, on a computer, the processing will happen in terms of numbers. Something will come out, and then you can decode it to print out the next word or token. So now here, instead of these tokens like apples, bananas, so I'll just say, okay, let's equivalently say the hidden rule that I'm trying to learn is that there is some linear function that maps the input vectors to the output vectors, and you give it the sequence of x1, y1, x2, y2, x3, and a question mark. And transformer should learn the hidden rule that it's a linear rule and output. So if you plot this, for instance, suppose I have this, I'm just visualizing, I'm giving, that's why, super, just two-dimensional information. X's are scalars and Y's are corresponding values. So it's just actually even one-dimensional if you want to look at just X's. And you see from the plot that, okay, a linear relation could explain what's going on. And you pass that data, but you pass the whole thing, that's the crux, okay? All the XYs are passed together as one sequence, as opposed to we pre-chopping them up and giving to standard self-supervised learner, standard supervised learner, okay? And then transformer, if it uncovers the hidden rule, then it should be able to use that hidden rule to predict yn plus for you. So the goal is clear, I hope. The goal is to predict the hidden label. It's actually a regression problem I'm gonna analyze given these pairs and the final query. And at this point, in case you feel confused that why is this any different from linear regression, is because the transformer needs to not really uncover a theta star for that particular sequence. It has to learn to be able to get a theta star for any kind of data. Okay, that's really the crux of what it means to learn an algorithm is I will look at bunch of randomly chosen linear regression tasks. Each different random task will have a different linear rule. And from these randomly chosen linear tasks, transformer learns how to solve linear tasks. And that's a really powerful thing, right? I'm giving as training examples, in some sense you can call it, several different related tasks, and there is an algorithmic way to solve the task in context learning, because transformer seems to be implementing an algorithm for solving a task rather than fitting just a parameter. That's why when you give it a new query from such a task, boom, it can actually do the task. Okay. So trying to understand in context learning of linear functions was originally motivated in this paper by Garg et al. It was pretty recent, but it's a fast-moving area. And then several follow-up researchers, they made a variety of complicated constructions to try to understand and explain why is a transformer doing this, how is it able to do that. But the constructions are quite complex, and it's not even clear that if you train a transformer, will it even reach that construction. By construction, I mean a complicated configuration of parameters of the whole transformer. And you train transformer using, say, Adam or something. Will the set of parameters transformer reaches, will it correspond to the complicated construction? Most likely no. So there was like a kind of big gap. And what we are trying to answer in our work is that not only, okay, other work shows that there exists this construction. What we are claiming is that actually when you train a transformer using a standard choice of method, it most likely leads to a configuration of parameters that actually performs in-context learning because it figures out how to implement gradient descent. And it's totally possible that, even up till this point, you may be still wondering, okay, what is really happening? So let me dive down further, more deep into this to give you like a very clear, crisp picture of what is really mean to learn gradient descent and to do in-context learning of linear functions. So as a warm-up, and that warm-up is the most I will actually get to in this talk because more advanced stuff is in subsequent papers, but the key ideas are already developed when talking about this warm-up. So what I mean by that is we'll analyze the ability of transformers to learn these linear functions in context. And we'll do that using the simplest kind of attention layer, which is called linear attention. So in attention, there is a softmax function. In case you don't know it, just keep that in mind. Others, you may have seen it in an implementation. There is a softmax function. If you remove that, you get what is called linear attention. It's called linear attention, but don't let that fool you into thinking that this is some kind of linear neural network, okay? In each attention layer, the data, whatever, the parameter comes in cubic because there's two arrows here and a third arrow here, and these are multiplication, and it's the same arrow coming in. So you can already imagine that there's each attention module is at least doing something cubic, and then you have a deep attention network. So it's highly nonlinear, even though the layer softmax I have removed for now, okay? And with that, you get linear transformer, and linear transformers are pretty powerful at quick learning linear relations already. And in fact, it turns out experimentally, you can see that linear transformers are actually better than transformers with the usual attention at learning linear function. But that's a side remark. So it's a non-trivial but important simplification so that we can start doing some mathematical analysis. So now we are ready to dive a bit deeper to try to see what does it mean for transformer to implement gradient descent in this linear model setup. So here I'm showing you a transformer with L attention layers. The input is this matrix Z, which contains XY pairs, X1, Y1, X2, Y2, call them demonstrations. Xn plus 1 is your query, and you put a 0 in there as your query. You don't know and the transformer's goal is to predict Yn plus 1. And what should our training objective be? It's a very natural training objective that I'm going to set up is you look at the prediction from the last layer and see how different it is from Yn plus 1, desired true label. You minimize the squared loss of that. And the minimization is over randomly chosen these pairs of inputs, where the relation between the inputs is over randomly chosen linear models. That's why I'm saying we are going to now train a transformer on a bunch of randomly chosen linear regression tasks. And this transformer is going to be able to then, as a result, be in a position to solve these linear regression tasks for any new input you can give it. And for a transformer, for each layer, some computation is happening. So you can extract, in some sense, the transformer's guess for the output, yn plus 1 from each layer. You can read it out. We'll call it prediction k as the transformer's prediction for yn plus 1, given the input z. All right. But before we kind of attack the transformer in detail, let's ask a very simple question. Given these n examples, how should we go about predicting yn plus 1, like in the most basic manner? Well, one of the most basic manner here is just, look at xy pairs, and we kind of are looking for linear model. That's what we are looking for, right? You fit the best theta hat that matches the xy pairs, and then use the best theta hat to do a prediction yn plus 1. That's one way. That's like a simplistic viewpoint, right? Well, to make it even more concrete, you could say, let's find the best theta hat. How should we find it? Well, let's find a theta hat that minimizes the empirical risk, right? Empirical loss. And to make it even more concrete, let's do this minimization using gradient descent. Okay, so you start at theta 0, you initialize it to something, and suppose you're running gradient descent on the empirical loss. You run one step, you run another step, and you keep running until you've gone through L steps, and you reach some gradient descent solution for theta. And now the most amazing thing that happens is what is the theoretical claim here, that our business was to predict yn plus 1. One way to do that would be to set up this regression loss, come up with a theta hat, use theta hat as the predictor, but come up with this theta hat by running L steps of gradient descent on this empirical loss. But this would be for a fixed linear model, right? And the most amazing thing that happens here now is we are actually not going to be running gradient descent on this empirical loss. We are going to be sending the matrix Z through the transformer. And what we are going to prove is really the heart of the claim of what the transformer is doing. And that's the theorem that suppose the data and the parameters, they follow some distributional model like here Gaussians, then there are stationary points, so where gradient is 0 of this loss of the training objective, so that the transformer's prediction at layer K, which is this object, matches the prediction that you would get from K steps of gradient descent. That's the amazing thing. So prediction 1 will be obtained by doing inner product of theta at 1 with xn plus 1. And prediction 1 looks at exactly what things look like if you had done one step of gradient descent. Similarly, prediction at layer 2 and prediction at layer L all the way. So this is what it really means, that our transformer has then implicitly learned to perform gradient descent, because when you read out its information, it's as if that theta had been obtained by running gradient descent. And thus you can see that transformer one layer is equivalent, one layer of attention is equivalent to figuring out how to do one step of gradient descent. One can make a stronger theorem about global minima, etc., but okay, let's not worry about that. And more interestingly, if the data geometry, if the data rather than coming from, nicely shaped Gaussian, if it comes from some arbitrary shaped object, which we roughly describe using a Gaussian with covariance sigma, and theta star is somehow well associated with that, then transformer works well even for this data, but now it uses its outputs of each layer. They're as if you were doing preconditioned gradient descent rather than gradient descent. Here are the preconditioned gradient descent iterations, where preconditioning basically means, you multiply the gradient with some with some positive definite matrix. Here, that positive definite matrix ends up being the inverse of sigma. So that means if data is badly conditioned, a tension layer will undo that badness and still manage to learn a good predictor for that, which is another very strong geometric property of the attention layer. So let me just visualize this for you, because this idea of learning gradient descent is really the key idea. And it should spark your imagination about figuring out attention layers that can learn other algorithms, or constructing your input data in a way that you can make transformer learn all sorts of other algorithms, or making some other assumptions on how the data and the models are distributed, and seeing that, oh, after all, preconditioned gradient descent here, this is with the fixed sigma, but this should remind us of Newton's method, right? So for gradient descent to Newton's method, maybe there are situations where you can actually formally say transformer can learn the famous Newton method, or transformer you could somehow, that one is an open question in case anybody wants to think about it. In optimization, so-called conjugate gradient method is very famous and well studied. Can transformer learn conjugate gradient? I mean, most likely it can, but one has to figure out how. And by how, I mean to do it mathematically provably, okay? Not, I mean, just empirically. Okay, so let me visualize this, what happened here. So on the x-axis, I'm training the transformer, and I'll train the transformer's weights, parameters, using any algorithm you want, Adam, LBFGS, Adam W, whatever. So x-axis is transformer weights. And now, given what I said, you can interpret the forward pass of the transformer as implementing some kind of algorithm. So when I just initialize the transformer's weights are random, so they're not at some stationary point of the training objective. So the forward pass can be interpreted as doing some algorithm, which is not yet gradient descent. So you can imagine it as if it's doing a random walk, it moves through space randomly. After you've trained transformer for a while, it already is implementing a method which is somewhat less random than a random walk, and making some progress. And you keep going through that. And it's, as you can see, it's now started to do some kind of descent towards the minimum. And as this process runs, eventually, once the transformer's weights have converged, they seem to correspond to having learned gradient descent. And that really is a very remarkable property. And you may think that, wow, okay, so one way to think about this is that as you train the transformer, it is moving through some kind of space of algorithms, starting from a random walk until the algorithms converge to gradient descent as the algorithm. That's what this linear attention transformer did. And then this viewpoint, you can think that this viewpoint, having gone through the theory, why is this so valuable is, as we saw, that in-context learning seems to be the crux of LLMs. And this explains that in-context learning could be explained, that LLMs are able to do in-context learning because the forward pass of a transformer can itself be interpreted as a learning algorithm. And as a result, when you give it an in-context input, it can output the right thing if it's doing good learning. And that really is, that's why a key to explaining this prediction power of LLMs. And as I said, prediction error of transformer is an approximate, easy to control through the gradient descent language. Several people have done that, trying to understand generalization theory and statistical guarantees. But this is, I think, for one layer. Wu et al. Have done that recently. And this thing that I kind of didn't go too deeply, but very interesting thing happened that, okay, transformers attention layer can also adapt to data geometry. And that's why the word geometry of attention is in there. Something that I haven't yet exploited is worth just throwing it out here for anybody in the audience who's interested. In fact, for this transformer, we proved that query matrix time key matrix approaches the inverse of the covariance for the entire transformer. Even if you have 100 layers, the product of query key tends to the same matrix for all the 100 layers, which suggests that in reality, for more complex data, there could be not only this conditioning happening, but a huge potential for weight sharing. And if we figure out how to realize that weight sharing for transformers, that would really speed up the training of large language models. So this geometric thinking can inspire many future things. So, and this is kind of lots of others ever since I made these slides. In the meanwhile, I think there are at least 4 new papers worth mentioning, but can't summarize all of archive for you. And now the final thing which is kind of the last message I want to give you is, just because we did analyze this linear transformers on this linear task in detail, doesn't mean that's all we can do. In fact, if you actually put back the softmax, so instead of linear attention, you get the regular good old attention layer. Can we also analyze that? And because that's the one that is being used in practice, can we analyze something about what is being used in practice? So the question becomes, can transformers with nonlinear architectures, which means nonlinear attention layer, also learn to implement algorithms for nonlinear data? And the answer is actually yes. It's it's a preprint of ours. Transformers implement functional gradient descent. And at a very hand-wavy level, what you can think is that the linear attention transformer on that linear regression task, or let's say minimizing squared loss type of task, ended up learning regular gradient descent. Nonlinear transformer will end up learning some kind of gradient descent in function space, where the function space is characterized by the nonlinearity in the attention layer. But the way of doing this proof really matches the proof structure of the linear transformer. That's why I just only went into the linear case. But it's a very cool realization that, okay, once there's a nonlinearity in the attention, as there always is, the forward pass is learning to do some kind of descent in function space. And one can even prove a statistical theorem, like if the data generation process, let's say the data is, if H is like some kind of kernel-like function or a covariance-like function, like in a Gaussian process or something else. So if the data is generated according to some statistical process, and the generator of that statistical process is the one sitting also as the nonlinearity in attention, then one can prove a theorem that as you make the transformer deeper and deeper, it approaches the base optimal learner. So essentially, statistically best possible learner for that type of data. But there is many more things in this paper, and this is a very fast-moving area where all kinds of interesting in-context learning theorems wait to be discovered, depending on what kind of nonlinear relations you may know about in the data that you think transformer can learn. So with that, I will actually stop my talk here, and I'm open for questions from the audience.
Yeah, that was a fantastic exposition to certain very interesting things. And it's good to see that the old things are coming back on the way.
Yes.
For example, this last one is quite interesting, that you get this RKHS metric or kernelization back for the nonlinear case.
Yeah. So softmax is not softmax won't do the RKHS, so one can prove the theorems even for softmax. But in case H corresponds to a kernel function, then the geometry is really of RKHS, which is very cool to have.
I think so. Audience, please, now the session is open for questioning. I think there is already one question on chat.
Okay, can you read it out? Because I'm not seeing the chat here right now.
Okay. So this question says, is the data geometry a collection of all points coming from the theta equations where you have applied the gradient descent? So it's asking about the data geometry. Yeah.
Okay, so I'll just answer broadly. The question is about roughly, I guess, person is trying to understand what do I really mean by data geometry. And for me, and there's a little bit of technicality maybe you saw in there. For data geometry, I really just mean the X vectors, how are they distributed in space? And if I just cover them with an ellipse corresponding to Gaussian, let's just call that data geometry. Of course, you could view it through a much more refined lens if you were to think distributionally. I just want to cover it with that Gaussian to make analysis easy. One technicality that is happening in there, if you look at it with the data geometry, I don't want to flip back and forth between too many slides lest there is confusion, but let's it was, I think, this slide is to be able to prove a strong theorem. There is a kind of closer relation between data geometry and the underlying unknown parameter space geometry. And as one develops this theory further, decoupling those further will be helpful or make the theory richer. So I hope that kind of answers the question.
So any other question from the audience, please? Okay, another question is here. Is there any geometric explanations why multi-head attention works better than single-head attention?
Geometric, I don't know, but you could, yeah, in the line of what I am talking, so maybe give us some more time. We are trying to see what happens to the theory when you try to write out the math with multi-head attention. But you can kind of see that, whenever you are learning some algorithm and there is more paths to go from input to output, that just makes the class of algorithms more powerful in some somewhat quantifiable sense. But yeah, we are thinking of trying to formalize this statement a bit more mathematically. Once that is done, then I'll have a more precise answer for you. But otherwise, you can always think, as you make the architecture more powerful, with multi-head, you're only a superset of single head, so hence yes. But can you formally say how much more powerful? Remains to be done. Unless ever since maybe in the past 3 days when I was on a plane, some new paper came on the archive, but I don't know. Most likely not.
So any further question, please? You can unmute yourself and ask question. Any further question, please?
Okay, seems
So,
like.
by the way, so I had a simple question that you are modeling it as a gradient descent on this extremely simple squared error kind of loss function.
Mm-hmm.
Why that simple function? I mean, for multi-head and other complicated forms of attention, don't you think that this function would also get complicated and might not
Yeah,
be modeled?
it would. So this is like just to, let's say, make mathematical analysis easier because gradient of squared functions are nice. But
Yeah.
if the goal was just this kind of regression type goal, then this is like a good regression loss function. If the goal is to understand learning of some task in context learning task that is not regression like, then you would like a classification like or some other task, then you may have to design a more suitable loss function and then see if one can carry out the math to prove that minimizing trying to minimize that loss function leads to learning a corresponding algorithm to solve that family of learning tasks, which may be different from regression.
And yeah, that is the second thing, that this whole modeling task for in-context learning depends on this regression setup.
Right.
But if you go to other sort of things, I mean, transformers became extremely popular because they could model the long-term dependency between two tokens
Mm-hmm.
between long text, and still it can better than LSTM and RNNs, it can capture the connection between those words separated by long texts.
Right.
And so when such things are coming, I think there is some attempt of using category theory for modeling these linguistic constructs,
Mm-hmm.
not in context to transformer. But when such language modeling things are coming, do you think this setup of in-context learning would still be useful?
Yeah, for sure, like as I kind of cited here on this motivating slide and this kind of related work, which that for many linguistic tasks, even those that are kind of capturing long context, I mean, this is still, I guess, called context, for token buffer.
Yes.
So the length of the context is some floating number. There is, in some sense, nothing that I fixed here about the length of the context. The important thing is that there is a context that helps sufficiently to concentrate the measure or to predict where the output should be. And being able to be sensitive to context is the crucial power of these LLMs. So the part that is still mathematically imprecise even now, uh, attention module is built to kind of manage this, dependency and whatever information, but there is no like crisp mathematical relation that how does attention formally capture uh, long range dependence, because these are all kind of
Exactly.
empirical just put together, but to try to turn that into mathematical theorem, uh,
Very tough.
potentially
It's
some
very tough.
language or some more advanced language from world of not
Mathematics
necessarily
needs to be
category
there.
theory, but is needed. Yeah.
But I mean, this is what you have shown is a very nice way of expressing the intuition. I mean, this empirical intuition in this particular setup. Uh, I mean, this might be the last one from my side. You are showing this regression loss function, which is uh, in a traditional setup kind of convex function, having only
Yeah.
one single minimum.
Yeah.
But very often, even in in-context learning, we have seen LLMs ending up for hallucinations. Hallucination means it's providing wrong answers, even
Yeah.
for
Yeah.
simple prompts. How do you see that? Is it something like a bad local minima is coming, something like that in loss function?
That's a very interesting question on how to view hallucination. And there is that like there are few factors at play. Let's say hallucination. So like suppose if you are talking about chat GPT or GPT-4 or
Yeah.
whatever, they were trained with a certain objective function. And when we are using them, we're trying to use them for all kinds of other tasks. So if you were to think that the theorem I showed, it said, okay, this transformer is trained on random regression tasks, and hence it provably learns an algorithm that can then solve all regression tasks. But if suppose I've trained it on some completely other types of tasks, then what kind of algorithm is it learning? And may that algorithm then, as a result, for an new input, be more prone to hallucinating? Because it's like if you were to almost this could be also a philosophical question that in generative AI, it's doing its job really well because it's generating stuff. You call it hallucination just because you happen to know additional information, whether this was a fact or not. But as far as the machine is concerned, it's actually doing a great job. It's generating stuff that looks like human language. So it's a
I
little
mean,
nailing it down
unless we have
mathematically
that
becomes
extra information, we cannot differentiate or call it hallucination. That's right.
exactly. And that's why when you want to write a mathematical theorem, then you have to capture that what would it mean? Like how are the distributions or how are things measurably different so that you can quantify, etc. But to me, I think, this hallucination is a proof that it's doing great job.
I mean, but it's a big trouble actually. So
It
I
is a
often
big
try
trouble,
to,
and that means one needs to actually, if you want to build LLMs that are robust against hallucination, then you have to have you have to take measures against that, because it's sort of like it's like a, a generative machine where like I mean, you can't just solve it through the lens of kind of robust training also, because you make a machine which is trying to solve all kinds of general language tasks, and in some tasks, those may look like hallucinations. Sometimes you may not, as a human, be able to judge whether this was a hallucination or not, because only if it's a known fact was it a hallucination. But suppose we're generating logical statements where it generates a logical statement which is essentially undecidable mathematically.
no, yeah, I mean, that is for logical statement or language, but in numerical cases, like you showed a numerical
Yeah,
example,
okay.
there it can also make a mistake actually. That's the
Yes,
point.
exactly. So there you can try to nail it down a bit better. So there's
Yeah,
some people are trying to see, can transformer by doing in context learning learn to do, for instance, basic algebra and arithmetic?
yeah,
And answer is actually yes, but in a very limited manner, because when some kind of sufficient distribution shift happens, and these are not yet quantified words, like suppose I train
right.
it on pairs of 2 and 3 digit numbers, but I ask it to do arithmetic with 6 digit numbers, most likely it'll generate nonsense. So that means it learned some pattern, but it didn't learn the addition algorithm. But it is entirely possible because it wasn't trained to do that thing. If I were to train a transformer to learn arithmetic algorithms, then maybe it will not fail. So this is the mismatch between training and testing in some sense.
Exactly.
So there was a quick question, I think in the audience. You talked about now I could actually see the chat because I did something.
Okay, yeah,
You talked
Arghya
about
has a
conjugate
question.
gradient. Can you tell something more about that? Where is it is being implemented? So conjugate gradient is a classical method in optimization, and it's provably uh, amongst the best, or probably the best, for minimizing quadratics, convex quadratics. So it does a certain set of updates which look a bit different from the vanilla gradient descent. And the question I had asked was, if my transformer with the kind of attention and the task I set up could learn gradient descent and preconditioned gradient descent, the question I asked was, can it learn some other fancy method also if you were to create a suitable task for it? Or you were to replace attention, the linear attention with some other fanciful attention, or I don't know. It's an open question. Couple of people in optimization that I talked with, they asked me this question also, because optimization people always ask about conjugate gradient. But if it's maybe in the audience, you can have a look at my paper and see how the math is done, and you can try to then look at conjugate gradient math and see how to connect the two. It's a nice project for sure.
Sir, can you just send the paper in the chat? It will help.
Okay, let me just put the link to the title is in the slides. Let me copy paste there. Actually, let me copy paste for you in the chat. My paper is just a sec. Okay, here is the paper for everybody. And the follow-up paper to this, which does nonlinear transformers, you will be able to find once you have found this paper. The Google Scholar can help you with the rest.
Yeah, I think that's sufficient. So if there are no
So I
further
have a
questions,
question, if it's not too late.
Anish, do you have a question?
Yeah, so I mean, this is the first time I'm seeing this. I mean, I haven't read your paper, but as far as I can understand, so what you're showing is that eventually the optimized parameter is somewhere near what gradient descent would might get, right? But it doesn't retrace the path gradient descent follows. Am I right in saying that?
Well, the thing is, see, gradient descent algorithm itself, when you run it, it's kind of an imprecise algorithm, right? Which only iteratively goes somewhere. So, and the error or mismatch for everything can be bounded. So I think numerically it's as good as running gradient descent at that point. And you'll see
Okay,
this
so
empirically. That's why I had a plot there that as you deepen the transformer, it does a more and more faithful thing, then up to some noise variance. But yeah, I
right,
think
so exactly. And my question is somewhat technical, and exactly at that point, do we have any theoretical bound to how much deviation we will experience in between? I mean, in the intermediate steps?
so. If you want to understand, I see. Yeah, okay. That's a very good question. I'll have to think about it. Like suppose I showed you that visualization that after at 0 steps of transformer, it's like random walk, after 30, 70, and it's converging. So
Right.
what is that in between stuff? So once we understand that in between stuff, like the rate at which we are going to gradient descent, that's a nice question. I may
Because if we stop, yeah, sure. I'm sorry to interrupt. Please go.
no. So I think you and I are on the same track here for this thing. What I don't know, if our current theorems I'll have to think about it. Can one easily pull that out or not? Roughly, the speed at which you're converging to the method of choice. So one way to do that as a byproduct is, for transformers, you can analyze the speed at which atom converges to stationary point of the transformers. That speed will be inherited into roughly saying how quickly through the space of algorithms are you coming close to gradient descent. So one can start formalizing and bounding those things.
Okay. So I have a second question. So you showed that the inner product, the inverse of the inner product with the weights is roughly equal to the inverse of the dispersion matrix, right?
Mm-hmm.
And in that sense, I mean, the basic assumption was you had the input data and the parameters drawn from Gaussians with parameter sigma. So
Yeah.
what if I mean, this falls in a very good sense because we already have the second moment somewhat uh, encapsulated by sigma. But what if the distribution is something like where moments do not exist exactly? For example, Cauchy.
Yeah,
And
that's
do you have any idea what happened?
yeah, that's an excellent question. Also, I think I remember in the world of optimization, I have worked for many years on heavy-tailed distributions, etc. And this is like okay, even like okay, there's no moment here. It is so. I think yeah, for this more interesting versions of data. A theorem remains to be written, but I think it is possible. One just has to set up the task correctly. And the reason for this is the following. Suppose your noise distribution, okay, is not say Cauchy, but like some alpha stable, something with some fractional moments are available, like less than maybe second moment, but 1.x. Then it seems like this Adam method that is widely used for training transformers, it seems, I mean, your question is going in a very important research direction, actually. The Adam method is primarily by far the most popular one for training transformers. And that's because Adam seems quite well suited to deal with heavy tail noise or other such difficult noise settings. So one may wonder, can I somehow say that my transformer with some instrumentation, instead of learning gradient descent, can it learn an Adam-like method? So it'll require some help to do that because it doesn't necessarily seem designed for that. This is the question I'd asked in the beginning, why is gradient descent falling out? Why not something else? And to some extent, we've set it up this way. But I think by looking at these more realistic noise assumptions, we'll get a deeper understanding of how a transformer can do something or what it can actually do. But yeah, this is fully the research edge. It's a very nice question.
Thank you.
Okay, so thank you, Suvrit, for taking part in all these stimulating discussions. And
I'll ask one last quick thing. Somebody's mentioned a keyword I like. Whether quantum
here is a
computing
question. Yes.
whether quantum computing has any impact for performance of transformer. Answer is not in the current sense, no, because current sense quantum people are crazy about I want to do these hard problems. And in neural network land, we are saying, fine, we'll have some non-convex problem. We may not even we won't ever reach a local minimum. We may not even reach a stationary point, yet this stuff can work. So even in the classical world, we are far from understanding things fully. Quantum thing I just view right now as speed up. However, that said, maybe there is some very interesting connections because there's a separate area called quantum machine learning. I think those guys know much more deeply about an answer to your question than I do. I'm only speaking from a distance. Okay, cool. That was a quick answer, but that's it.
Thank you so much, Suvrit. So although you cannot hear our claps, but let us heartily thank you, express
Thank
our
you.
gratitude for taking part in this session, and maybe see you
My
sometimes
pleasure.
next
And
other
yeah,
iterations. And if possible, sometime we would be very happy to actually physically invite you to Indian Statistical Institute.
yeah,
This is one of the pioneering research institutes in statistics, started in 1930. And showed the path of statistical research in all over Asia, founded by Professor Prashanto Chandra Mahalanobis, in whose name,
yeah.
we
I know the
famous.
history of ISI actually a little bit.
Yes, right.
I used to work a lot on Mahalanobis distances once upon a
Mahalanobis
time. So I
distances,
looked where is the
disparate
name coming
function.
from and so on. Yeah. No, it's ISI has a very strong reputation. Yeah. Someday when travels permit me, I will be very happy to
Yeah,
come and
we
meet
will
in
also be
person.
very happy to host you. Okay, so thank you everyone. That's where the session ends. Have a nice time.
Thank you. Bye-bye.